Thank you for this invitation and this opportunity to share power domination with you guys. So let me start. I'm going to start directly on this because I don't want to waste any time. And so let's start here. So I'm going to start with this update. And basically what I wanted to show you, it was the new problems that we've been having and things that we're doing nowadays on power domination. When you work on applications, one of the beautiful things about working with applications is that things change. Things change very quickly because technology changes, and so that is a very nice way of keeping always something something new to work on. So I'm having here. So let me start by saying, I'm going to introduce really quickly power domination for those of you who are not familiar with this concept. So power domination is a form of graph searching proposed as a model from for the monitoring process of electrical power networks. So I'm going to start with a little bit of electrical engineering, although that's not my expertise, so I'm going to share enough as to get a sense of the problem. So in electrical power networks need continuous monitoring, so we don't have blackouts, power surges initially, and as they become more complex, the monitoring of power networks requires more and more tasks. So monitor a power network means knowing the electricity wave at any network point at any single time in real time. So this is accomplished by placing phasor measurement units. These devices measure the phase angle and the magnitude of the electromagnetic waves in the place of the network where they are placed, but also can provide information for other locations. And the idea is that it's not necessary to put a PMU in each node of the network. That is not necessary and it would be too expensive. So we put PMUs at some places, and then we combine the readings of these PMUs with Kirchhoff's laws and obtain the information at any other nodes without a PMU. So the monitoring process, in a nutshell, works like this. We have a set of PMUs that are strategically placed at selected network locations so that they provide enough information to reconstruct the electromagnetic wave at any node without a PMU. And they have to be synchronized because we want real-time information. So basically, there is a process in which we are constantly reading and calculating new values. So the PMU placement problem in electrical engineering consists of, for one side, we want to find, we want to have enough information, right? So we need a certain number of PMUs. But at the same time, PMUs are expensive, especially when this problem was proposed, and especially the first PMU that is placed in an area, because a PMU for work requires certain infrastructure. So normally a PMU could cost between $40,000 and $200,000. So it depends on the infrastructure that is necessary to install the PMU in that place. Now, we're into graph theory, so let's leave aside the engineering for a while, and let's just focus on the translation of this problem into graph theory. So the translation was done in this paper, right? In 2002, they introduced power domination so that when a graph is modeling an electrical power network, what would be a power dominating set in the graph, so a solution to a power domination problem for the graph, corresponds to a solution for the PMU placement problem on the network. So the definition presented here, this is an excellent paper. I really like this paper, and it's they contain many nice results, but their definition is closer to the electrical engineering part and talks a lot about edges and vertices of the graphs. So later, these authors published this other paper in which they simplified the definition and is only given in terms of vertices. In fact, people were already using it because it was kind of clear, but they were the ones who gave a good proof of the equivalence between both definitions. And this is the definition I'm going to present today. So the definition is just something very simple. We have in a simple graph, and by simple I mean it has to be finite, no loops, no multiple edges. So let's start by there, and we say that a set of vertices, select a set of vertices, and we're gonna define the vertices observed by that set of vertices. So you can think of the vertices in the set S as vertices with a PMU in the electrical power network, and then think about vertices that are observed as vertices for which these PMUs provide measurement. So the first rule says that all vertices in S and their neighbors are observed, and any other vertex is non-observed. This rule is applied once at the beginning of the process. And then we proceed iterating this rule, which says every vertex who is the only non-observed neighbor of an observed vertex becomes observed. And this can be think about, well, let me just show you, because I had here a little figure to show you how these rules are applied. So suppose that we have this graph here, and we start with, this is the vertex B, and this is the set S. And I'm gonna represent the vertices that are observed with a bold dot, and then the other ones with a white dot. And so initially, when I apply rule number 1, it says that every vertex in S and their neighbors are observed. So after rule number 1, all of these vertices are observed. Now rule number 2 says every vertex who is the only non-observed neighbor of an observed vertex. Well, basically we have only 2 non-observed vertices. This one doesn't have any observed vertex, but this one has 2 neighbors, and basically this one also has 2 neighbors, and this is the only unobserved neighbor of this vertex. So this one becomes observed. And then we iterate the rule, and by iterating the rule, we can observe this other vertex, and therefore, in this case, we can conclude that the set S is a power dominating set of this graph because all of the vertices are observed at the end, right? So again, this corresponds to placing a PMU. If this were an electrical power network, we would place a PMU in this location, and that would be it. We didn't need any more. I'm going to show you some more interesting examples as well, right? And but first, I wanted to give you a more formal definition of power domination. Normally, we define it in terms of sets, and we have a set that is increasingly we iterate the number of vertices that are observed. So the power domination number of a graph is the minimum cardinality of a power dominating set. So that's the goal of the problem, minimizing the cardinality of a power dominating set. And notice that by now you should know that after all I explained about electrical power networks, right? The power of power domination refers to the application on power systems, while the domination part on the name refers to the first rule, because basically when every vertex is observed after the application of rule number 1, then we have that S is a dominating set of the graph, right? So the first step in this process is domination. And later on, we're gonna see what happens with the second step. So for the time being, I wanted to show you some interesting examples. And actually, this example was the one that got me interested in power domination. I was listening to a talk, and I started playing with this example, and I really liked. And this is what I tell you what I really like about this example. Notice that here, if I start with this vertex in this corner, and I apply rule number 1, and I have all of these vertices observed. Then I apply rule number 2, and these 2 vertices in the corner have only one non-observed neighbor, so that neighbor becomes observed. And then once I have an entire column basically here, then the next one follows through, right? And then this is, for example, is showing that this grid, the 3 by 5, has power domination number 1, but in general, you can say that any grid of 3 by n for any positive integer n will have power domination number 1. And that is something very different than domination. Domination doesn't happen in that way. So that was something that attracted me to this problem. And in fact, with any grid, right, it happens that if you can suppose that all of these vertices in the grid is a Cartesian product of 2 paths. So if you pick a path, either one or the other, right? You can choose any of the 2 paths, and then eventually every vertex is observed. Therefore, to observe the Cartesian product of 2 paths is sufficient to dominate one copy. If we can dominate one copy, then we can propagate to all the vertices in the graph. And I became interested in this problem, and I observed that this not only happens here, but it also happens if instead of 2 paths, we have 2 cycles. And in this case, we have a torus. But if we have 2 cycles, then the only difference is that in this case, we need a double. I mean, we need 2 paths, 2 cycles, either horizontal or vertical, but we need 2 because the degree is larger in this case. In the case of the grid, we were playing with the fact that we have some vertices of degree 3. In this case, every vertex has degree 4, so we have to have 2. But it happens the same thing. And in this case, I didn't even have to put the dots because it filled up really quickly. So, and not only this, this also happens naturally if it happens in the product of 2 cycles, the product of 2 paths. It's expected that it will happen also in a cylinder, the Cartesian product of a path and a cycle. So it happens the same thing, except that in the cylinder, we have to choose again, like basically due to the symmetry in the case of the grid and the rectangular grid and the torus, we just choose the minimum between n and n. And in this case, it's a little bit different because when we do it by a cycle, we just pick one of the cycles in the top of the bottom, while if we pick one of the paths that determines the height of the cylinder, we need to pick 2. Right? So again, depending on if you have a taller or cylinder with a bigger girth, you will choose one or the other. So these results, those were some of the first results on power domination. I know these ones very well because as I told you, I became very interested in the grid, and I was writing the paper. I listened to a talk in 2005, and when I was writing the paper, I realized that this paper appeared, and they had already proved it. So that was when I said, well, maybe I can reuse the research I have done for cylinders, tori, and so on. So we obtained these other results. So that was some of the first work in power domination. And until then, power domination was studied by computer scientists as an algorithmic process, electrical engineering who do a lot of simulations, and in graph theory. Now in graph theory, there were many results in structural graph theory for particular families of graphs. And all of them follow the same pattern as they prove for rectangular grids, cylinders, and tori. So the idea is you select a general graph of the family and find a good candidate for power dominating set of minimum cardinality. This part is fun, right? Because it's like a fun game, actually. You can explain it to many people and it's easy to get engaged into it. But then you have to prove that that is indeed a power dominating set. And that part is also usually easy because you have seen that it works, you have some intuition. Now, the hard part is usually to show that that is the best possible cardinality for a power dominating set. That is to show that any set of vertices of the graph having less vertices than your candidate for minimum power dominating set is not a power dominating set. So that process is usually long, very technical, and not elegant at all, because one starts playing with many different things. So after I have done 2 or 3 papers on different families of graphs like that way, I said, okay, I'm done with this. There has to be a better approach. And what we are lacking here is some theory. We need to find some lower bounds for the power domination number. We had upper bounds, but we didn't have any lower bounds. Of course, from the electrical engineering point of view, upper bounds are a lot more interesting because they tell them, you know, this is the worst case that you can have. But lower bounds are necessary too in order to find perfect solutions or good solutions. So that is what brought me to other forms of graph searching, right? And in particular to zero forcing. So I'm going to start moving towards the second part of my talk, which is a little bit of basic relationships between power domination and other forms of graph searching. So I'm going to show you here the definition of zero forcing, and then I'm going to explain something else. Zero forcing was introduced in this paper, and it's a very long number of authors, so they even established a group, and they are recognized as an author right now. So the idea of zero forcing is this. If we have a graph, and we have a set of vertices, we say that that set T, say, is a zero forcing set if after the following coloring process, all vertices of G are blue. So the idea is that initially all vertices in T are blue and all the remaining vertices are white. And then we iterate the following rule that says, if U is the only white neighbor of a blue vertex V, then U becomes blue. And this rule is iterated until there are no longer, it does no longer produce additional blue vertices. So the zero forcing number of a graph is defined as the minimum cardinality of a zero forcing set. So the idea is compare the definitions of zero forcing set and power dominating set, right? So basically in one case, we're saying, well, what we want is every vertex in T are blue and the remaining ones are in black, are white. And then we iterate this rule. In this case, we say L vertices in S and also their neighbors are observed. And then we iterate this rule. But if you compare the rules, right, either the observation rules for power domination or the color changing rules for power domination, right, it's very clear that if you change the white with non-observed and blue with observed, the second rule coincides in zero forcing and in power domination. So the only difference is in rule number 1, and it follows very clearly that if a set S is a power dominating set of a graph G, then the close neighborhood of S is a zero forcing set of G. So how can we use this? How can we exploit this? So the idea was to say, well, if I have a graph with a power dominating set S that is a minimum power dominating set, so this is the power domination number of G is exactly the cardinality of S. By the previous observation, we know that the close neighborhood of S is a zero forcing set. And then by definition of zero forcing set, any zero forcing set in a graph G has to have cardinality at least the zero forcing number. So we have this inequality, and we also know that if delta is the maximum degree of a graph G, then the close neighborhood of the set S will have at most this number of vertices. And since we were taking a set with cardinality equal to the power domination number of G, now we have this. And observe that from this inequality and this one, we have a relationship now between the zero forcing number and the power domination number. So that is a first step. Unfortunately, we do have found this is not good enough for simplifying the proofs on power domination. Normally, what I was observing when I was working with this bound is this bound exceeds in 1 unit, basically it's 1 unit less than what we wanted. So we said, well, what's the problem? So eventually we figured it out and we were able to improve the bound to this. And this bound was the first time that somebody used the relationship between power domination and zero forcing as a tool to analyze both problems and joining results from linear algebra and from graph theory, find new results in both of the areas. So the idea here for this bound gives us a new way to combine linear algebra tools and graph theory, and this lower bound streamlines some of the heavy technical parts of the proof for power domination. And I'm talking about proofs that were reduced from 5 pages to 3 lines. So it does have a significant advancement. And also it shows, it's more conceptual, it's more elegant, it shows really what is going on. I have an idea to show you the how this bound is obtained, but I'm afraid that since we started late, I'm gonna try to skip this. Should I skip it, or that way I can finish on time?
You should go ahead and talk about it. I think as long as it won't take a few more minutes, it's fine.
It's a simple idea, and this is the funniest thing, how simple the idea is and how powerful it is. So the idea is, if I have a power dominating set, and suppose that I have a vertex S in the power dominating set. So basically, I don't need to include the entire S and the entire neighborhood of S. I can include just one less vertex, because then this one will observe this one, right? So the only thing I needed to show is, instead of having to add delta plus 1 vertices, I only add delta. This one I don't need it. I can always remove one vertex. Now, I cannot remove any one vertex, right? Because I could have things like this. And then if I remove this one to account for S and this one to account for T, then I'm having troubles because they both end up lacking one vertex. So the idea is that we show that this cannot happen in a power dominating set, in a minimum power dominating set, because every vertex in a minimum power dominating set has to have an external private neighbor. Therefore, there is one vertex that you can remove and safely remove. So with that, we were able to prove this bound. And with this bound, we now have a bound that works. And as I was telling you, many of the proofs, the proofs for grids, Cartesian products in general, were significantly reduced in length and made much more elegant. Now, the problem we have is that from the complexity point of view, calculating the zero forcing number and calculating the power domination number is pretty much the same. So the bound is not useful unless we know the the zero forcing number or the power domination number. So in that paper in the Australasian journal, in this, we exploited that for many families. But then what happens when we don't know it? So in this case, we have to go back a little bit to the history of zero forcing. And how was zero forcing introduced? Zero forcing, as I mentioned, was introduced in this paper. And the idea was to relate it with the matrices associated by a graph, associated to the graph. So if we have a graph, suppose the vertex set is B1 through Bn, and we say that the matrices described by the graph are all of the symmetric real matrices, say, that such that the pattern of zeros in such matrix is determined by the non-adjacent vertices in the graph. So the adjacency matrix that we all know is a particular matrix here, but if the ones are replaced with any other positive integer, as long as you keep the symmetry, the matrix remains having certain properties that are interesting, and that's why this class A of G is studied. So the class of matrices described by a graph. And in particular, for this class of matrices, it is defined the maximum nullity and the minimum rank. So as expected, and since the matrices are symmetric, rank minimization is exactly the same as maximization of the nullity. And notice that even the title says zero forcings and the minimum rank of graphs. Their goal was to bound the minimum rank of graphs. And indeed, the zero forcing number, the definition of zero forcing number guarantees that in any graph, the maximum nullity is a lower bound for the zero forcing number. And with this, we start to get more excited because now we have a tool that is independent of the zero forcing number and is significantly different because it's a tool belonging to linear algebra. So it gives us another angle from where to tackle the problem of power domination. So using our theorem, we said, well, if I divide the zero forcing by the maximum degree, I obtain a lower bound. But if I divide the maximum nullity, I have the same inequality. And in particular, since we're graph theorists, we're thinking, well, let's just use the adjacency matrix. And in many cases, this bound was providing the exact value of the power domination number. So I always liked this work because it was, you know, in linear algebra, people had the lower bound and they wanted to find the upper bound. And in graph theory, with graph theory tools, it's fun and it's easy to find the upper bound. The trouble we were having was with the lower bound, that is what they had. So it was beneficial for both fields. And since then, power domination and zero forcing have been studied together. And that relation that we show between power domination and zero forcing also extends to directed graphs, and it also extends to a relation between generalizations of K forcing and generalization of such as K power domination. Basically, I'm going to skip introducing these definitions because we are kind of over the time, but and I want to focus on the update part of this problem, but it's a very interesting property. So, in order to talk about current challenges and current problems on power domination, I need to go back to electrical engineering. As I said, some of the applications that have appeared from, for PMUs. So basically in 2010, there was a large scale deployment of PMUs in all North America. And since then, people have been learning. And what initially was thought that it was important to have the minimum number of PMUs, that was because of cost. Now, people have realized that minimizing the PMUs produces unsatisfactory results, mainly due to the lack of redundancy to recover data lost in the event of failures. And then they have also observed that in cases where they just place a few more additional PMUs, the results are significantly better. So basically it offsets, the advantages offset the increased costs. And also it's been observed that there are other applications and other uses for the data of PMUs. As networks become more complex and they start integrating different types of energy, and people, you know, people who have solar panels, for example, or start producing at the same time that they are using electricity from the power system. So the data from PMUs can really be used to enhance the quality of the service in many ways. So this is important, and since it has more uses, it justifies the cost. And finally, another issue that has influenced the current problems with PMUs is the development of the micro PMU, which is a cost-effective alternative to a PMU, practically inexpensive. So some desirable solutions to the PMU placement correspond to non-minimal solutions to the power dominating set. So what we're trying to do now is to say, well, what happens when one of more transmission lines fail? How can we make sure that we have a PMU placement such that even in the event of a certain number of failures of the transmission lines, we can recover the data? Or, for example, what happens if somebody tries to inject malicious data into a PMU? And that could be done, and that is something that we need to do to protect the infrastructure. So then, basically, all of those problems reduce to the idea of how do we determine how many units is reasonable, how many additional PMUs is reasonable to place, and where to place them in order to maximize the results. So this is what the current research in power domination is. And I'm going to stop here because I'm realizing that I went over my time. So I wanted to stop here.
Great, thank you so much, Daniela. It was a wonderful talk. So we have some time now for questions from the audience. If people would like to ask a question, if you could just unmute yourself, unmute your video, and maybe tell us who you are and where you're from. So I actually have a question, Daniela. So things like domination, the domination number is not really well understood for many graph families. The one that I was kind of surprised to learn about a while back was hypercubes, that we don't know the exact value of the domination number for hypercubes. Do we know much about gamma p for various graph families? You mentioned grids and cylinders and things, but other kinds of families of graphs?
We do, surprisingly. And in fact, we know a lot, and I would say that somehow we know more about power domination than about domination, precisely because of the link with linear algebra. In domination, there are some problems where you do have, you can easily find a good set that you can, even in the hypercube is a great example for what you said, right? Because you can find sets that are really good, but how do you prove that that's possible? And that is complicated because, even though that is the most surprising case to me, and I feel that the case of the hypercube should be completely solved. But yes, we know more about gamma p than we know about gamma. And that is surprising. And I